Welcome back to part 2 of the Unit 3 Skill 1 video notes, where we will go back and revisit examples 1 and 2 to fill out these charts that contain the defining characteristics for the equations that we graphed in the previous video. So I'm back here at example 1, and this was the original equation, 1 divided by x minus 2 plus 5. And I am going to find the intercepts for that, the domain and range for that, increasing, decreasing intervals, rate of change, and whether or not it's 1-to-1. We already determined the horizontal asymptote and vertical asymptote of this graph in the previous video, as well as the point of symmetry, which is just h and k. So I'm going to go straight actually to domain and range because it has to do with those asymptotes and the point of symmetry. So for both the domain and range, we will start both of those by saying all real numbers. Because if you look at the graph is pretty smooth and includes almost all of the x values as I move to the left and right. Like almost all of those x values have matching y values that belong with them, except for one. There's just one value of x that is where the vertical asymptote is, where the graph breaks at that one particular value of x, so basically x can't be 2. At that one value of x, there is no matching y value. The y value doesn't exist when x is 2, because if I plug 2 into the denominator, I get a 0. And 1 over 0 is technically undefined. And so therefore, there is no output. There's no y value that matches that x. And so therefore, that x is left out of the domain. But because every other x, like 1, 0, -1, and so on, and then 3, 4, 5, and so on, every other x easily has matching y values. That's why we just write all of the real numbers with the exception of x equals -2. And that'll always be where the vertical asymptote is. The vertical asymptote is the one value of x that's left out of the domain. And then similarly for the range, the one y value that we exclude is where the horizontal asymptote is, where basically what k is. So maybe I'll write that. So the value of h, whatever h is in the AHK formula, is what is left out of the domain, and then the value of k from the AHK formula is what is left out of the range. The reason why y is not going to ever be 5 is because the fraction that comes before 5, 1 over x minus 2, is never going to be 0, right? 1 divided by something can never equal 0. It will get very close to 0. We kind of looked at that yesterday right here. If I plug in really large values for x, so down here and over here, then the denominator of that fraction becomes infinity, so then the fraction part itself gets closer to 0. Never exactly equals 0, but gets close to 0. And then when you add 5, that value gets close to 5, infinitely close to 5, right? These are wanting to go to 5 and equal 5, but they never actually will. Y will never actually end up equaling 5. And so for that reason, it's left out of the range. But every other y value going up this way, 6, 7, 8, and so on, and then all the y values going down, 4, 3, 2, so on. Those are all included in the graph and all included in the range. So that's why we tend to use this notation. All of the real numbers except 2 for the domain, all the real numbers except 5 for the range. Now, for increasing and decreasing, we always have to read the graph from left to right. So from negative infinity toward infinity. And of course, we see the graph breaks at 2, so that'll be a point where our intervals break as well. So if I look at this graph, as x goes from negative infinity toward 2, as it moves from left to right, the corresponding y values are going down. So we would say that they are decreasing from the x values of negative infinity to 2. And then the graph breaks, so we use a separate interval to talk about the other part. So as x goes from 2 to infinity, again, we see those corresponding y values go down. They decrease. So x is going from left to right, 2 toward infinity. The y values are decreasing. So 2 toward infinity is my other interval for where the y values are decreasing. And then because we think of both of these parts as decreasing, then the function is never actually increasing. For the rate of change, we just basically say that that will vary because it's not a linear function. The graph curves. So the slopes between different points are different. It's not the same slope, not the same rate of change. So that will vary. And we say yes, the function is one-to-one because it passes the horizontal line test. If I draw a horizontal line through any part of this graph, it will only hit the graph one time. So yes, the function is one-to-one. So now for the harder part, obviously, right? Intercepts are always the hardest part. Let's go ahead and start with X Intercept. Basically what I have to do to find the X Intercept is plug in 0 for Y and solve for X. So I'm going to carve some space out. So for my X Intercept, I plug in 0 for Y, and my goal is to solve for X, isolate X. So if you recall, and when we did this with other functions, we were always trying to sort of isolate the function part, like the part with X in it, get that by itself, and then eventually isolate X. So it's going to be the same here. I'm going to subtract 5 from both sides. I'll think of it as -5/1. And so if I do that, I get -5/1 on the left and then 1/x minus 2 on the right. And what I have here is what we call a proportion, one fraction equal to another one, that we can solve through cross multiplying. Multiply this to that and set it equal to the product of 1 and 1. So I get -5 times x minus 2 equals 1 times 1. And then now it's a simple linear equation. I just distribute the -5 and isolate x. So I'm going to subtract 10 from both sides. I get -5x equals -9. And then I divide both sides by -5. So I end up with x is equal to positive 9/5 or 1.8, whichever value you prefer. And so let's write that here. So my x-intercept is 1.8, 0. And if you look back at the graph, if I extend the graph more, it does look like it would hit the x-axis at a value that is very close to, but not quite equal to 2. So 1.8 makes sense if I look at my graph. It's always good for us to check the reasonableness of our answers. Now for the y-intercept, the idea is to plug in 0 for x to see what you get for y, which is always a little bit easier because y is already solved for. So I just evaluate what it would be if x is 0. So I plug in 0 for x. And so that leaves me with 1 divided by -2 plus 5. And 1 divided by -2 is basically -1/2. Plus 5 would be 4.5. So that number is my y-intercept. So the coordinates for that would be 0, 4 and 1/2 for my y-intercept for this graph. And then if you look at the graph, that looks like it's correct, right? 1, 2, 3, 4.5. That value was also in our table of values here that I erased earlier. Let's take a look at number 2. So again, with example 2, yesterday we did the graph of example 2, and we also figured out what the vertical asymptote would be, what the horizontal asymptote would be, and also what our point of symmetry was. So those parts are done. So now what we're going to do is look at the rest, and specifically I'll start with domain and range because it has to do with the horizontal and vertical asymptotes. So the domain will be all of the real numbers except for the one that created a vertical asymptote, the one that created a 0 in the denominator. If you look at your graph, that's right where the graph breaks, right? It was smooth and connected everywhere to the left of 0 and everywhere to the right of 0, but right at 0 is where there's this huge break and also where there is no matching y value. So we leave that out of our domain. Similarly, our range will include all of the y values, all these values up here and all those values down there, except for the one that y never equals, which is where the horizontal asymptote is, which is at -4. The graph will get close to -4. It'll ride up alongside it very closely on both sides, but it'll never actually ever get there, so that value is just not a part of our range. Now this graph, because it had a vertical reflection, the boomerangs, if you will, are facing opposite directions. So this time they are actually increasing instead of decreasing. So for this one, we would put, it's just not decreasing, not applicable. So remember, for increasing, decreasing, we always read the graph from left to right. So this would be from negative infinity toward infinity. So you look at it going that way, and where the graph breaks is at x equals 0. So as x heads from negative infinity toward 0, the y values that match those x's are going up. They are increasing over that interval from negative infinity to 0. Similarly, for the other part of the graph, as x moves toward the right from 0 toward infinity, the y values that correspond with those x's are going up. Again, they are also increasing. So we basically have two answers for increasing, two intervals where the matching y values are going up, and no intervals where the matching y values are going down. Also, because this is not a linear function, the rates of change are not constant. They vary from point to point, so we'll just put varies. And yes, the graph is one-to-one because it passes the horizontal line test. If I run a horizontal line at any point on this graph, I will only intersect it one time. What that means is I only ever have one x for each y. Even right here, so because we have to remember the graph is moving at an angle, so even right here, if I drew a horizontal line, it would technically only be hitting the graph one time, like right there. And same here, because it's always moving at a slight angle. So if I draw a horizontal line through it, it would technically only be hitting right about there. So it passes the horizontal line test, therefore, yes, it is one-to-one. Okay, so like example 1, I'm going to move this table of values out of the way so that I can do some work to find my x and y-intercept. So to find the x-intercept, I basically have to plug in 0 for y. So I would get 0 is equal to negative 3 over x minus 4. And then my job is to solve for x. I plug in 0 for y, solve for x. And in doing so, I begin first by sort of isolating the fraction part. So I'm going to start by adding 4 to the other side. And I'll think of it as 4 over 1 is equal to the now isolated fraction. Once you've isolated the fraction, we have created a proportion, right? Two fractions equal to each other. So we can solve for x by cross multiplication. So I can do 4 times x equals 1 times negative 3, which is negative 3. And then I just need to isolate x, and I do that by dividing by 4. So I end up with x equals negative 3 over 4. So that'll be my x-intercept. And if I look on the graph, that looks about right. Like right where it's hitting the x-axis right here, looks like it's between 0 and negative 1, not quite at negative 1 yet, so negative 3/4 makes sense. For the y-intercept, I have to plug in 0 for x. So I get negative 3 over 0 minus 4. But as we talked about yesterday, if you divide by 0, that value doesn't exist. In fact, that's why there's a vertical asymptote there, is because when x is 0, the whole denominator is 0, and then when that happens, y is undefined. So this whole value is actually undefined, so the y-intercept doesn't exist. There is no value for y for when x is 0 in this particular case, because there's a vertical asymptote along the y-axis. What I'd like you to do now is try to see if you can determine the values of all of these defining characteristics for numbers 3 and 4. So pause your video here, try these, and check if they're right when you're done. All right, let's check and see how you did. So the graph of number 3, we have y equals 4 over x minus 2 plus 1. And yesterday, or not yesterday, in the previous video, we had found already the vertical horizontal asymptote as well as the point of symmetry. But if for the rest of these, you should have an x-intercept of negative 2. You can find that by plugging in 0 for y, isolating the fraction, cross-multiplying, and isolating x. And then you can check it over here with the graph and see if it makes sense, and it does. Looks like it's hitting the x-axis around negative 2. For the y-intercept, you can plug in 0 for x and just simply evaluate. 4 divided by negative 2 is negative 2, plus 1 is negative 1. And also you can see that point is right here on our graph as well. Then for the domain, it's all of the real numbers except where the vertical asymptote is, so x can't be 2. For the range, it's all of the real numbers except where the horizontal asymptote is, so y can't be 1. This graph is similar to the parent graph. It's got a boomerang on the top right and then 1 on the bottom left. So it's decreasing for both intervals. So it's from -infinity to 2 where the graph breaks, and then again from 2 to infinity, and then it's never increasing. Rate of change varies because it's curvy, and it is 1-to-1 because it passes the horizontal line test. Then in number 4, in the previous video, we had found the vertical and horizontal asymptotes were both at 0, and the point of symmetry was 0, 0. So we had already determined that, and our job today was to find intercepts, domain range, and the rest. Well, this one is is very similar to the parent function in that it has an asymptote on both axes, the x and y axis. So it has neither an x nor a y-intercept, so those were easy in a sense. The domain is all of the real numbers except where the vertical asymptote is, so that's at 0, and so x can't be 0. The range is all of the real numbers except where the horizontal asymptote is, which was also at 0, so y is never going to get to 0. It's going to get really close and want to be 0, but it'll never actually technically equal 0, so that value is left out of the range. This graph, like the last one, is similar to the parent function. It has the positive boomerang in the top right and the -1 in the bottom left, so both sides decrease. So from -infinity to where it breaks at 0 decreases, and then on the other side from 0 to infinity it decreases as well and never increases. The rate of change will vary because the graph is curvy, not sharp or linear, and it is 1-to-1, yes, because it passes the horizontal line test. So I hope that you had matching answers, but if not, you get a chance in class to practice tomorrow and ask and answer questions, and I will see you there.